The JavaScript event loop. If you've ever worked with JavaScript, you've probably heard this term whispered in hushed, slightly terrified tones. It has this reputation for being incredibly complex, right? But what if I told you it's actually a pretty simple, even elegant solution to one of JavaScript's biggest headaches? Let's actually demystify this thing once and for all. So let's start at the beginning. Why do we even need an event loop in the first place? Well, it all comes down to a core feature, or you could say a limitation of JavaScript itself. We have all been there. You're on a website, you click something, and nothing. The whole page just locks up. You can't scroll, you can't click anything else, the animations stop, it's totally frozen. That incredibly frustrating experience is the exact problem that the event loop was designed to solve. And the reason for that freeze, it's because JavaScript is single-threaded. You can think of it like a chef who can only cook one meal at a time. That chef has a to-do list, which we call the call stack, and they can only ever work on whatever single task is at the very top of that list. One thing and one thing only. Now, for simple, quick tasks, this works just fine. A function gets added or pushed to the top of the stack, the JavaScript engine runs it, and then it's removed or popped off the stack. Then it moves on to the next one. It's a last-in, first-out system. Simple, predictable. So far, so good. But what happens when we give our chef an order that takes a really long time? Like a complex data calculation or fetching a huge file from a slow server? What happens when our one-task-at-a-time chef has to bake a cake that takes an hour? Total gridlock. That's what happens. The call stack gets blocked. That long-running task just sits there at the top, hogging all the attention. And until it's finished and popped off, absolutely nothing else can run. No user clicks, no animations, nothing. Your user is just staring at a dead page. This is the fundamental problem we need to solve. So how do we get around this? How does our chef handle the hour-long cake without making every other customer wait? Well, turns out the chef isn't working alone. The browser itself steps in and gives JavaScript some amazing superpowers. And these superpowers are called web APIs. Now, this is a really important point. These are not part of the JavaScript engine itself. They're extra tools provided by the browser environment. So when you call something like setTimeout or make a fetch request, you're essentially telling JavaScript, hey, hand this slow task off to the browser to manage. Just let me know when it's done. And boom, the call stack is immediately free to handle other work. Okay, so the browser finishes the task, the timer ends, the data comes back. Now what? Where does the completed work go? It can't just shove its way back onto the call stack. Instead, the result, usually a callback function, is sent to a waiting area. It's like a line at the bank, and it's called the task queue. So now we have our busy call stack doing its thing, and this line of finished tasks waiting patiently in the task queue. How do we connect them? This is where the star of the show, the event loop, finally makes its entrance. Its job is incredibly simple, but so important. Think of it like a bouncer at a club. It's constantly watching the main stage, the call stack, and it asks one question over and over. Is the stage empty? The moment the answer is yes, it lets the very first task from the waiting line onto the stage to be executed. In understanding this busts a huge myth about setTimeout. When you write setTimeout with a delay of, say, 1,000 milliseconds, you're not saying, run this code in exactly 1 second. No, you're saying, wait at least 1 second, and then please add my callback to the waiting line. If the call stack is blocked for another 5 seconds doing heavy work, your callback is just going to sit in that queue waiting its turn, even though its timer finished ages ago. Okay, you with me so far? We've got the call stack, the web APIs, and the task queue. It seems pretty straightforward. But just to keep things interesting, modern JavaScript introduced a bit of a plot twist. It created a new, high-priority express lane for certain tasks. See, as our applications got more complex with promises and async await, we realized some async tasks are just more urgent than others. For example, updating the UI right after you fetch data should probably happen before some non-critical setTimeout you scheduled. We needed a VIP lane. And that VIP lane is called the microtask queue. Think of it like the fast pass line at a theme park. When a promise resolves, its .then or .catch handler doesn't go to the back of the regular line. Oh no, it gets an express pass straight into this special high-priority queue. Now, listen up, because this is the single most important rule of this whole system. Our bouncer, the event loop,
always checks the VIP line, the microtask queue, first. But it's not just one from VIP, one from regular. The rule is absolute. The event loop will process every single thing in the microtask queue until it is completely empty. Only then, once the VIP line is totally clear, will it even consider taking just one task from the regular old task queue. Now, this absolute priority has a dangerous side. What if a microtask creates another microtask, and that one creates another? Well, you can get into a loop where the event loop is stuck forever servicing the VIP line. This is called starvation, because the regular task queue never gets a chance to run. Your clicks, your timers, they're all stuck waiting for a turn that may never come. All right, that was a lot, I know, but we have all the pieces of the puzzle now. The call stack, the regular task queue, and the super important microtask queue. So are you ready to put all this knowledge to the test? Let's have a little showdown. Take a look at this code. We've thrown a little bit of everything in here. We've got a promise, a tick setTimeout, a queue microtask that then queues up another one, and just a plain console.log. It's a perfect storm to test our understanding. So, the big question is, based on everything we've just learned, what's the final output going to be? In what order will these numbers appear in the console? Take a second, think it through. What's the priority? All right, ready? Let's walk through it. The very first thing that logs is number 5. Of course, it's synchronous code sitting right in the main script. It gets pushed onto the call stack and runs immediately before any queues are even checked. So 5 is logged and the main script is done. The call stack is now clear. Okay, the stack is empty, so our event loop bouncer gets to work. First stop, the VIP line, the microtask queue. It sees the promises.then handler, pulls it, and runs it. Boom, we log 1. Is the queue empty? Nope. It finds the first queue microtask, runs it, and we log 3. But wait, that task just added another microtask to the queue. The event loop doesn't care. Its rule is to empty the queue, so it immediately grabs that new task, runs it, and logs 4. Now the microtask queue is finally empty. So, with the call stack empty and the VIP line clear, finally, the event loop can check the regular task queue. What's been waiting patiently this whole time? Our setTimeout callback. It finally gets its turn, moves to the stack, and logs 2. So the final order is 5, 1, 3, 4, 2. Did you get it right? Let's just recap those rules one last time because they're so important. 1. Synchronous code is king. It always runs first. 2. Web APIs handle async stuff for us in the background. 3. Promises and their buddies go to the high-priority microtask queue. 4. setTimeout and other callbacks go to the regular task queue. And the golden rule, number 5, the event loop empties the entire microtask queue before it will even consider touching a single item from the task queue. And there you have it. The event loop isn't some unpredictable magic. It's just a system with a very clear, very strict set of priorities. So the next time you're staring at an async bug and the timing just feels off, you don't have to guess anymore. You now have the mental model to trace exactly what's happening and why. The only question is, now that you know the rules of the game, how are you going to use them to solve your next async bug?